So I'm really excited to introduce Beryl Sui, who's going to present her work on high-rate convolutional codes with CRC-Aided list decoding for short block lengths. And this work actually is the result of a sustained effort. So Beryl led a team of undergraduate researchers to develop a high-rate list decoder based on a dual trellis Viterbi decoder, which was, I think it's just been a really fun project, and Beryl has done a fantastic job with it. So let's go ahead and listen to Beryl's ICC talk.
Thank you, Professor Wessel. So hello, everyone. Today I'm giving a presentation about the recent paper accepted to ICC 2022, and the title is High-Rate Convolutional Codes with CRC-Aided list decoding for short block length. And I want to thank all my co-authors, Henry, Brandon, Ava, and Professor Wessel for their help with this project. So in the recent years, there has been a renewed interest in designing powerful short block length code. And some examples are shown in the table. For example, there are the tail-biting convolutional codes with wraparound Viterbi algorithm, the extended BCH codes with order statistics decoding, the LDPC codes with FFT-based belief propagation decoder, also polar codes and PAC codes with their corresponding decoders. And yeah, in recent paper, Yang et al. Proposed the CRC-Aided CC as a powerful short block length code for binary input AWGN channels. And the convolutional encoder is either zero terminated or tail biting with rate 1 over omega. And given a specific CC, an effective CRC is constructed by searching for the distance spectrum optimal, or DSO, CRC polynomial. And I'll talk about this in detail soon. And then the DSO CRC polynomial and the convolutional encoder is concatenated together, and as shown on the in the diagram on the right. The code words are then BPSK modulated and transmitted through an AWGN channel. And the SNR is defined as 10 log the BPSK amplitude in dB. The nature of concatenation permits the use of SLVD, which is serial list Viterbi decoding, and it's very effective at low error probability and gives a small expected list rank. The SLVD finds not just the most likely path, but it also outputs the decoding results, a result path based on the path likelihood. What about the higher rate? So in this paper, we consider designing CRC-Aided ZTCCs and TBCCs for higher rates at short block length for the binary input AWGN channel. And we consider systematic rate omega minus 1 over omega convolutional encoders designed by Lin and Costello. So there are 3 main contributions of this paper. First is that we designed the DSO CRC polynomials for rate omega minus 1 over omega ZTCCs and TBCCs at short block length. And we combine the dual trellis with SLVD to achieve a low complexity decoding. We also analyze decoding performance and complexity for these codes. So to start, I will introduce the dual trellis structure, which we used instead of the primo trellis in Viterbi decoding. On the left is a primo trellis for rate 3 over 4 with 2 memory elements. And we can see that for rate omega minus 1 over omega encoding in general, performing SLVD over the primo trellis is highly complex because there will be 2 to the omega minus 1 outgoing branches, so 8 in our example. So how can we reduce the complexity? And so we can use a dual trellis, which was proposed by Yamada et al. In 1983. The dual trellis is constructed using the parity check matrix. And in the dual trellis, there are only 2 outgoing branches at each state, which makes the comparison of path metrics less complex. The state of the dual trellis is represented by the partial sums of the v+1 adders in the observer canonical form of the parity check matrix. And thus the number of states doubles in the dual trellis than in a primo trellis. And the state evolves in terms of output bits yk. Because each bit of yk is either 0 or 1, there are at most 2 incoming branches at each state. And in the beginning, there are only 2 to the v states. At each state, we determine the next state from the next bit of the output and the corresponding parity check matrix polynomial. And at the last bit of the output, we do a right shift to make all the paths go back to one of the initial states. And we repeat the construction for n over omega times to obtain the full trellis. For decoding DTCCs, we only need some additional steps to go back to the 0 state. And for each state, there is a code sequence that can bring it back to the 0 state. But for decoding TBCCs, we add a root node for the SLVD. And this additional root node makes keeping track of the path metrics and finding the suboptimal path easier. And we check the tail biting condition after finding each path. And next, I will talk about design of the DSO CRC polynomials. So we assume the states are in order from 1 to n, i.e. the irreducible error events, has the same starting and ending state sigma, and they don't pass the state smaller than sigma. Then we construct the ZT and TB path using the IEs as building blocks. And the length of this path are n over omega, and output weight is less than d tilde. So lastly, we find the degree m CRC polynomial that can get rid of the most IEs, which is the DSO CRC. And since we're interested in a low target error probability, the DSO CRC will be the CRC with the max D mean. And here we show the DSO CRC polynomials we designed for both rate 3/4 DTCCs and TB 8 bits. And the degree of CRCs ranges from 3 to 10. And the number of memory elements are 4, 5, and 6. So we simulated the following plots based on these codes. First is the FER versus SNR for the CRC DTCCs with increasing CRC degrees of 3, 6, and 10, and a fixed block length of n equals to 128 bits. And the encoder has 6 memory elements, and it's of rate 3/4. And we can see that at the target FER of 10 to the -4, increasing the CRC degree reduces the gap to the RCU bound greatly. And with m equal to 10 and v equals to 6, the CRC DTCC approaches the RCU bound within 0.25 dB. And the next figure shows the FER versus SNR for those 3 CRC TBCCs at block length of n equals to 128. And the encoder polynomial is the same as the DTCC, and the CRC degrees are also 3, 6, and 10 corresponding. And at the same target FER of 10 to the -4, the SNR gap to the RCU bound is reduced to 0.1 dB for the CRC TBCC with m equals to 10. And this last figure shows the trade-off between the expected lead strength and the FER of the TBCC. And we can see that the expected lead strength is less than 7 for achieving the target FER of 10 to the -4 for all three CRCs. And for CRCs of degree 6 and 10, the expected lead strengths are very close to 1. And this implies a low average decoding complexity of the SLVD. And now I'll go on to the complexity analysis. So same as Yang et al., we use a red black tree SLVD, and the complexity of which is made up by 3 parts. First is the complexity of the standard self-Viterbi, and then the complexity of additional traceback operations required by SLVD. And lastly, the complexity of inserting new elements to maintain an ordered list of path metric difference. And in the table, EI denotes the average number of insertions which when decoding, and the C1 and C2 are computed specific constants, and we assume them to be 1 in our simulation. So using the equations in the previous slide, we calculate the complexity of SLVD for CRC DTCC codes and CRC TBCC codes, and plot them against the gap to RCU bound at target FER of 10 to the -4. The figure shows the performance complexity trade-off, and the data points of the same color corresponding to DSO CRC polynomials with degree of 3 to 10 for specific CRC-CC. And the red colors represent CRC TBCCs, the blue colors represent CRC DTCCs. For specific DTCC, the complexity only increases slightly as we get remarkable improvement on the gap to RCU bound. But when we increase the number of memory elements, the complexity increases a lot. The CRC DTCC with the best performance is about 0.22 dB from the RCU bound. And CRC TBCCs perform much better than CRC DTCCs because they avoid the termination overhead. For specific TBCC, there's a significant increase to complexity when we increase either V or M. And this is due to not knowing the exact starting and ending state when decoding. and the best performance of the CRC TBCCs is 0.1 dB to the RCU bond. And we can see that adding 1 bit to the CRC can improve the FER more than adding an additional memory element to the CC does. So the two main key takeaways for this paper are that the dual trellis can significantly reduce the LVD complexity, and for high-rate CC, the design paradigm of CC-CRC still can help us approach the RCU bond at low decoding complexity. And that's it. Thank you, and I will take any questions now.
Thank you, Beryl. I'm really excited about this work. I feel like, well, let's see, do we have any questions from the audience? So I feel like there are we've kind of stumbled across some open areas.
Mm-hmm.
So what do you think are the areas where we still have some things to figure out?
I think we definitely can simulate the ZTCCs with higher degree CRCs and see how they perform. And Henry is help us running to find the DSO CRCs on his computer, and we will see if it can produce any results, or it also fails because the memory issue.
Because it's interesting. The ZTCCs are worse, but the line is still vertical. So we wanted to go have some larger CRCs, but it gets harder and harder to find those CRCs of larger degree.
Yes.
So, Hung-Jae, what do you think is there something we can do to improve our algorithm to be more efficient, or we've squeezed everything we can and it just takes a big computer?
I think we have tried our best. It's just that when you increase the D2 a little bit, then the number of ZT path increases dramatically.
So I'd like to go back to the slide where you showed the list size.
Okay. Yeah.
Yeah. So this list size includes paths that are not tail biting paths, right? Because of the way that we.
Yes.
And I just wanted to mention, I don't think he could make it this morning, but I'll make sure he watches your recording. That the other, Chester is also looking at list decoding. He's going to build an FPGA list decoder, and we're trying to think about the right architecture.
Okay.
And one of the central questions that I've asked him to look at before because he's going to use the serial list decoder.
Yes.
I think for an FPGA implementation, we're going to use a parallel list decoder. And there are sort of two approaches, just like you. There's a choice between whether we're just going to keep all the paths and check for tail biting, just like we check for a CRC, or make sure that the only paths that we consider are tail biting paths, which is much harder, but then leads to a much smaller list size. And just yesterday, I was meeting with him, and what's interesting is in this approach, how very few of these paths that are on the list are tail biting paths. Did you even look at that? Do you know for your data, like what percentage of the paths that you considered passed the tail biting requirement, and then you went on to check the CRC? Or it's just something there was no reason for us to look at that.
Yeah, like I take a look, like when I was maybe debugging my code and just doing the like increasing the list size one by one. But yeah, the percentage of the tail biting path in all the paths is not that high, and I often got them like killed because they are not tail biting path. Yeah,
we had a conjecture that actually, it's very likely that the true transmitted path will be on the list, and that is a tail biting path. But all the other paths, we have a conjecture that the probability that they're a tail biting path, in other words, the probability that the ending state matches the beginning state, is roughly 1 over the number of beginning states. In other words, it's just totally random because those paths are essentially junk, right? There's no, it's just, you're looking at something that's wrong and comparing it to figure out like whether or not, what's the best wrong path. And so with that in mind, the complexity of there might be a real benefit to doing the work of ensuring that the only paths you consider are tail biting paths. And then your list size, because that's a big, if you go to your equation, the list size is a big part of the complexity, right? The complexity grows. We don't really have the equation shown here, but you know that, oh yeah, you do. So the C list it goes as, I guess it's the list size?
It's the number of insertions.
Insertions, okay. And how does the number of insertions, is L the list size?
Yeah, EL is the list size. So.
And oh, I see. The expected in number of insertions goes as the list size. It's linear in the list size. It's K plus M times the list size. Okay. So, oh, I see. But larger with the TBCC approach.
Yes.
Anyway, so I guess it's something, I guess what I'm saying is that I'm going to try to merge the two. So I think that, you and Ava and Brendan, we want to sort of bring you together with Chester as we move forward. Actually, I was thinking that since Chester is focusing on parallel list decoding, and you guys are focusing on serial list decoding, and what we'd like to do is write a paper that kind of goes through all of these approaches and figures out like, okay, what do I, there's a sense in which we feel like a serial list decoder with a maximum list size gives us the best performance. But it's also kind of a difficult thing to implement and rather complex. And Bill Ryan, who's been, Jacob King's talk last week, he used a parallel list decoder because it's easier. And so we want to figure out like, well, how much do I lose by using a parallel list decoder instead of a serial list decoder? And how big should my list size be for the parallel list decoder? That's where we started looking at this question of, well, do we want to restrict ourselves to tail biting codes? Anyway, I think that's something for the future for the group, that we want to form sort of an overall list decoding group. We can write that journal paper. And then that's kind of a separate endeavor that will let us compare, even though Chester is looking at low rate and you're looking at high rate. Actually, I think the list decoder, once you've written a list decoding program, whether it's high rate or low rate, is kind of not that different. That's not the hard part.
Yes.
It was the hard part until you implemented the dual trellis decoder, but now we have both of those.
Yes.
Great. So any other questions that people would like to ask?
I don't have a question, but I have some small comments.
Okay.
So on page 8, can we go to page 8?
Yes.
So the second bullet, it should be at most 2 outgoing branches, because you can see that in some states we only have 1.
Yes. Okay.
And on page 26, then when you talk about CRC-ZTCC, do not add the word code, because the last C already stands for code.
Okay.
Yeah. And then on page 27, the second bullet, it should be CRC-CC.
Oh, sorry. Yeah, that's a typo there.
Or you should say CRC-Aided CC. Yeah, that's the formal name.
Okay. Thank you.
Yeah, that's it.
Thanks, Hung Jae. Hey, Lin Fong, I have a question for you. Can you show us your, Beryl, take us back to the plot that has frame error rate versus SNR, where yeah, that one. Okay, so we think that, there's sort of a banana where the peel of the banana is the random coding union bound and the meta-converse bound. And as long as we're in the banana, we're happy. Now, recently, Lin Fong has refined the sphere packing bound. And I was just wondering, Lin Fong, do you think the sphere packing bound would be better than the meta-converse bound now that we have it? Or do you have it for the binary input, or is it only for additive, Gaussian input?
So the sphere packing bound is independent it's not dependent to the modulation scheme.
Lovely. Okay. So maybe we should, since you went to the trouble, which I'm so happy that you did, of reading that paper and implementing the sphere packing bound, do you want to see if it's better than the meta-converse bound in this case?
Yeah.
Great. I think that would be a great thing for us to see. I did see, I guess at the end of the day, our largest V was what?
6.
Yeah, V equals 6, which is pretty small. But we decided we were happy with it because it seemed like we were performing well enough. But when I look at this curve, you can see that we're peeling off at the low frame error rates. So I kind of feel like we might want to look at, and we are not restricted to multiples of 3. Like we could do V equals 7 and V equals 8. Isn't that right?
Yeah, we also did V equals 4 and 5.
Right. So I guess that's another area where I think Ava and Brendan could help us out and also Hung Jae, our team. We could design, what do you think, Hung Jae? Should we look at V equals 7 and see if we can get better performance at 10 to the minus 4 and 10 to the minus 5? I expect we would.
Yeah, we can try it.
Okay. Yeah, these are things that, and if you want, like I say, Beryl has a team, and if you want to sort of give instructions about how to run the code to find the CRCs, I think that would be really great for our journal paper, which I feel, so I feel like we're very close. So in other words, I'd like to submit a journal paper for Beryl, Ava, and Brendan, and Hung Jae, but by the end of the spring quarter, and I think that that's one easy thing that we could do, is to look at those a little bit more powerful, because frankly, V equals 6 is on the low complexity side. It's just that it worked so well that we thought, okay, that's fine. But looking at this plot, I'm kind of like, yeah, 1/10 of a dB is pretty small, but you can see that it's peeling away, and you feel like we could do better. So I think we should, as we've done with the other codes, it would just make sense to look at 7 and 8. I'm not even that, for completeness, we might want to build a huge table that we have like in the archive version of the paper for 3, 4, and 5, but I'm mostly interested in 7 and 8. And that might even solve maybe we don't have to go to higher CRCs and instead focus on slightly higher higher complexity convolutional codes, which, Hung Jae, are you confident that if we did V equals 7, we could get M equals 1 through 10?
Let me try it and I will let you know.
Okay. All right. Okay. Well, Beryl, this is a great talk and great work. Yeah, I think this is also the beginning of I think you should get in touch with Lin Fong and start learning a little bit about LDPC.
Yes.
And then later, I'm actually, this is like my worst time of the year as associate dean, but I've got admissions going on for both undergraduate and graduate and a variety of other things. But in a couple of weeks, I think I'd like to get Samira and Beryl together to form a group around this topic of flash memory. And we can start sort of the discussion about like what it is we're trying to do and how you guys can work together. I sort of think we want to have I was sort of thinking there could be conference papers that each of you write, and then we merge together into a journal paper sometime in the fall. So we'll talk about that. But I think that it's, I think we have that wonderful thing that that professors like to have a merging of a source of funding from SK hynix and good research problems. Okay, all right. So thanks everybody. And I hope you guys have a wonderful weekend. And we'll see you next time. Bye-bye.
Thank
Bye.
you.